Hello. Last time we started looking at general system of n degrees of freedom. Okay, a natural system which we had defined last time, and we assumed that there is a point of equilibrium, and we were expanding the terms in the Lagrangian, the kinetic energy term and the potential energy term, around that point of equilibrium. Okay, now this point of equilibrium could be stable, could be unstable, and that information will be encoded in the potential energy matrix, right? The Uij term, the Uijs, which we wrote down last time. And then we did some truncation in the Lagrangian. So we approximated, we did a Taylor expansion around the origin where we had chosen the point of equilibrium. Okay, and then we truncated the series in such a manner that the equations of motion that you get are linear, and that was left as an exercise to be done by the viewer, which maybe I can do once, maybe in the next lecture. And then we wrote down Lagrangian with under that approximation. So let me write down by summarizing what we did, and then we proceed from there. So we are looking at oscillations. Okay, so recap. First, we are looking at a system of n degrees of freedom. Okay, and then we assume that there is a point of equilibrium of the system, and we have chosen that to be at the origin. Okay, we also put the potential energy to be 0 there. That's the choice we made. So U at 0, by this 0 I mean all the coordinates take value 0, has been chosen to be 0. And the fact that that point is a point of equilibrium meant that the derivatives del U over del Qi, they vanished there. That's what we derived as a condition. Okay, and under linear approximation, for the equations of motion, I believe that you have already done that exercise. We wrote down that the Lagrangian becomes the following. It becomes half Tij Qi dot Qj dot, and you have summation over all I and j running from 1 to n, and then you have minus half Uij Qi Qj. Okay, where Tijs and Uijs, they are constants. Now we have already expanded about the origin, and we also know that our T, sometimes I'll write T and U to mean these two things, or maybe let me just write down Tij and Uij are symmetric, are real symmetric matrices. Okay, that's good. Now also recall that I did not make any assumption about this Uij. Remember, this was appearing as a second order term in Qi's, right? The first term was U of 0 and the second term involved del u over del qi, this one which went to 0, and this was the first non-zero term. Okay, so depending on what these coefficients are doing, what values they take, the point could be a stable equilibrium, unstable equilibrium, or whatever. Okay, so that information is coded in here. So as far as this where we stand, I'm not necessarily making an assumption that I am near a stable equilibrium. This could very well be a unstable equilibrium point. Okay, but for now we will pretend as if we are near a stable equilibrium and proceed, and later we will also talk about unstable equilibrium. Okay, let's see. Okay, so I was saying last time before closing that the moment we see these two quadratic forms, so as you might have already noticed that we have two quadratic forms here. Okay, and immediately we want to ask whether these two quadratic forms, whether we can say whether these are positive definite or no such property can be ascribed. Okay, so we want to know about their definite properties. Now what I'm going to show is, which is quite easy, that the first quadratic form, this one, is a positive definite quadratic form. Okay, and it's quite easy to understand. What do I mean by saying it's a positive definite quadratic form? It means that no matter what these column vectors and these row vectors, see, this you can write as a row, so you can write as a T as a matrix, a row from left and a column from right, right? That's what you can do. So what we are really asking is whether this form takes a positive value no matter what row and columns you choose. I mean, the row and the columns are related because they are transpose of each other. If it is never 0 and if it is always positive, then it will be a positive quadratic form. And that's what I'm going to argue, which is fairly simple. Maybe I can write down. So we are looking at the quadratic form Q Tij Qi dot Qj dot. That's what we are talking about. And you have a summation over I and j. Okay. Now remember how you arrived at this term. This gives you the, this was the kinetic term in the Lagrangian to begin with, and you have done some approximation, and this is what you have. Now if this represents kinetic energy, then if these velocities are not 0, okay, if your system is really, if your coordinates are really moving, they have some velocity, then the kinetic energy has to be positive, right? No matter what those velocities are, because it's a kinetic energy. Remember, kinetic energy is this. It's a sum of all these positive numbers, and that has what has that, and this is what has become this. Okay, so no matter what Qi dots you take, this is always going to give a positive value. So this is positive for all non-vanishing Qi dots, right? The only way this will give you a 0 is if the velocities of all of them, all of the generalized coordinates are 0. That is the only case in which you can say the kinetic energy is 0. But then that's not how you talk about a quadratic form. You talk about non-zero vectors. Okay, so whenever your vector Qi dot is non-zero, this will be positive. So I have argued that this quadratic form is positive definite. And this is very, very nice, because the moment I can say this, that this is positive definite, I go back to what we were talking about, simultaneous diagonalization of two quadratic forms, okay, and see that I will be able to not only put this in diagonal form with unit coefficients, but also simultaneously diagonalize the quadratic form corresponding to the potential term. Okay, so by this I mean I can simultaneously diagonalize, or let's say simultaneously put the two quadratic forms as sum of squares. Sum of squares. So my Lagrangian now becomes the following. Okay, so my Lagrangian becomes the following. Okay, so the fact that I can put as sum of square means that I will be able to do a transformation and go from the small q's here to some new set of coordinates, let's call them capital Qi's, okay, such that the following holds true. So sum of squares, so first one will be with unit coefficients. I'll put half anyway outside, that I can retain, there's no problem. So I'm saying this piece is being put as sum of quadratic squares with unit coefficients. Now there is no j because these are squares. Qi dot square 1 2 and your n degrees of freedom minus half okay. So under this approximation which we have made, the linear approximation, I have been able to write down my Lagrangian using a new set of generalized coordinate capital Q's in this form. And this is very, very nice result. Do you understand why this is very nice, what we have achieved? Let me put it slightly differently. Let me write it in this way. Okay, 1 to n half Qi dot square minus half lambda I Qi square. Do you appreciate why this is so nice? You see, what it means is that my system, upon choosing this new set of generalized coordinates, appears as a collection of one-dimensional systems which are not interacting with each other. Let me write it down. This means we have cast our system now this is not a nice sentence. Let's say upon choosing Qi Qi's as our new generalized coordinates. Okay. The system has become a set of n one-dimensional non-interacting systems. Has become a set of n non-interacting one-dimensional systems. And why are they not interacting? Because there are no terms which couple Qi to Qj. So there is no cross term between Qi and Qj. So there is nothing like Q1 and Q2 are couple. So when you are writing down the equations of motion for Qi, it will not get any contribution which will have a Q j appearing in it. So let's say you are writing for Q1. From this Euler, you write down the Euler-Lagrange equations. Let's say for Q1, that will not involve Q2. So meaning no matter what Q2 is doing, Q1 does what it has to do. Okay, so they are really independent of each other, and that's what I mean by saying that these are n non-interacting one-dimensional systems. So actually, this is very, very nice because one-dimensional systems are easy to understand. Okay, and this is what I have achieved. Let me see what else I wanted to say. Okay. Now our task is to first identify what kind of system, this one-dimensional system, these are. They are all going to behave same way. Then the only thing which will be different between any two different system, let me write down again. Let me write it down. It will be easier to say what I am saying. So L is, let's say, half Q1 dot square minus half lambda 1 Q square Q1. Okay, so that's one piece. Then you have half Q2 dot square half lambda 2 Q2 square and so forth. Okay, that's what our Lagrangian is. So if I know about this system, this one-dimensional system, let me call this L1, then I will know everything about this system also, because it's just n copies of this system. The only thing different between this and this is the lambda 1 here and lambda 2 here and all these coefficients, right? Other than that, there is no difference between these different dimensional one-dimensional systems. Now what controls these lambdas? It is controlled by the matrix U. Where is that? Here. See, those lambdas are the eigenvalues of this matrix U, right? So it is the matrix U which controls them. So we would be interested in knowing more about lambda. So lambda I are controlled or determined, let's say, by the matrix Uij. That's one thing. So we need to figure out what are the possible lambda i's. Okay, and of course this will depend on properties of uij, which is also tied to whether the equilibrium is stable or unstable, right? So that is one thing we want to see in the next video. And yeah, and let me just tell what these coordinates are called. These coordinates qi are called the normal coordinates. Okay, that's good. Now let's say you are given two different systems, and you choose some coordinates, some normal coordinates, which I have just now mentioned here, and put the Lagrangians of both these two systems in this form, in this manner. Okay. Now if you do so, what will be different between these two systems? It will be just the lambda i's, right? So it is just the matrix U which is going to differentiate between this system, between one and between and the other one. Okay, so we need to know a little more about these lambdas. That's what we will do next time, and I hope you already know, but anyway I will do it next time, that this is the Lagrangian of a simple harmonic oscillator if lambda is positive. Okay, I believe I have derived this or talked about this earlier, but in case not, I will do it in the next video. Okay, so as far as if lambdas are positive, then this system has become a set of n non-interacting one-dimensional simple harmonic oscillators. Okay, which is a very nice result. Okay, so we'll continue next time with more details, but you can already start imagining the following. Let's say I can choose to set my system in motion in such a way that not all the normal coordinates are moving. So not all of them start moving, only some of them, or let's say only one of them starts moving, right? And all other coordinates stay put, they don't move. Okay, and this way you can isolate the motion of one of these oscillators. Okay, meaning you can excite, let me use the word excite, you can choose to excite one of the oscillators and keeping all other oscillators silent, they don't move. Okay, they don't oscillate. So this you can do. Okay, we'll talk about these things in more detail in the next video. See you then.